In the previous episode, we talked with my professor about the concept of nothingness from a philosophical perspective. We questioned what nothingness means and explored that thin line between existence and non-existence. Now we are moving to a more scientific perspective. In this episode, we will discuss what quantum physics tells us about nothingness, quantum vacuum, vacuum fluctuations, and their connection to the formation of the universe. In other words, we are stepping beyond philosophy into the realm of physics.
Professor, was there really a nothingness before the beginning of the universe?
To understand that, we first need to unpack the concept of nothingness. In everyday language, nothingness suggests a completely empty space, a state where there is no matter or energy. But modern physics does not accept such a definition of absolute nothingness. In quantum mechanics, even if there are no particles in a system, that space is not truly empty. Even in empty space, there exists a form of energy called vacuum energy. This energy cannot be zero because of Heisenberg's uncertainty principle. Energy and time are one of the uncertainty pairs, meaning you cannot say with certainty that the energy value is exactly zero over a given period. This implies that even a vacuum is actually a seething sea of energy. Quantum electrodynamics illustrates this beautifully. In a vacuum, even though it seems like nothing exists, virtual particle pairs, such as an electron and a positron, momentarily appear and then annihilate each other. These pairs are called virtual because they are not permanent, they cannot be directly measured, but their effects are observable. The Casimir effect is proof of this. If you place two parallel metal plates close together in a vacuum, the vacuum energy between them differs from the surrounding vacuum energy, and as a result, the plates are pulled toward each other. This demonstrates that a vacuum is far from being truly empty. So what we think of as nothingness is, from the perspective of quantum physics, actually a field full of potential, what we call the quantum vacuum. In this vacuum, there are energy fluctuations, virtual particle pairs, and a constant bubbling. This bubbling means that even the fabric of spacetime itself vibrates at the most fundamental scales. And here arises the real question. If the quantum vacuum is already something, how did our universe emerge from this seething energy? That's where the real debate begins.
Professor, you said that the quantum vacuum isn't empty and that it's bubbling with energy. But can these fluctuations really lead to the formation of an entire universe? How could such a tiny event produce such an immense outcome?
That's a very good question. This is precisely where the phenomenon we call vacuum fluctuations comes into play. According to quantum field theory, vacuum energy isn't homogeneous. In other words, the energy distribution isn't constant throughout spacetime. These fluctuations occur continuously on microscopic scales. Within fractions of a trillionth of a second, energy can suddenly spike and drop. Normally, these are temporary, self-balancing events with no lasting effects. But think about it. What if one of these transient fluctuations reaches an extraordinarily high energy density? Some cosmologists suggest that such an extreme energy concentration could create a bubble of energy that begins expanding on its own. This bubble, through a process called cosmic inflation, could rapidly grow to become a universe in its own right. In other words, the Big Bang might have been the result of just such a quantum fluctuation. To understand this, we can recall the Higgs field. The Higgs field also contains potential energy in the vacuum, and its instability led to dramatic changes in the early universe. Similarly, an instability in vacuum energy, what we call zero-point fluctuations, could cause some of these events to become permanent. This provides a mechanism powerful enough to allow a universe to arise spontaneously. Some physicists call this vacuum decay. If the vacuum's energy suddenly transitions to a lower state, a process known as false vacuum to true vacuum transition, an enormous release of energy occurs. This energy could trigger the expansion of spacetime and give rise to an entirely new cosmos. Here's the critical point. The question of why our universe formed still remains unanswered. Quantum fluctuations could spawn an infinite number of bubble universes, but ours turned out to be stable enough to support life. This has led some physicists to the anthropic principle. Perhaps we live in a universe with conditions suitable for observers like us, because only such a universe could be observed in the first place. So while quantum fluctuations seem like a microscopic phenomenon, they have the potential to create a domino effect on a cosmic scale. The origin of the Big Bang might indeed lie in these quantum-level vibrations.
Professor, in the previous episode, we discussed how fluctuations in the quantum vacuum could be powerful enough to create a universe. But what about these virtual particles we often hear about? Do they really exist?
Virtual particles occupy a fascinating place in quantum physics. What we call the vacuum isn't absolute nothingness. Rather, it's a field teeming with constant energy fluctuations. During these fluctuations, particle-antiparticle pairs, such as an electron and a positron, spontaneously emerge and then quickly annihilate each other. We call them virtual because they aren't permanent. They can't be directly detected by an observer, yet their effects can be observed experimentally. One of the clearest examples is the Casimir effect. The attractive force between two metal plates placed in a vacuum demonstrates the presence of virtual particles in the surrounding space. This phenomenon is one of the key pieces of evidence showing that even empty space is actually filled with energy. Virtual particles offer a crucial window into understanding the fundamental fabric of the universe.
I understand, Professor, but how exactly are these virtual particles linked to the birth of the universe?
Because these virtual particles and their associated fluctuations create microscopic distortions in the fabric of spacetime itself. Imagine at the Planck scale, about 10 to the negative 35 meters, spacetime isn't smooth and flat. Instead, as John Wheeler described, it resembles a quantum foam, a constantly shifting, wrinkling surface where tiny tunnels and bubbles form and disappear moment to moment. This foamy structure acts like a stage where virtual particles are continuously popping in and out of existence. If one of these small-scale fluctuations reaches an extraordinary energy level, it could trigger an expansion that evolves into its own cosmos. In other words, virtual particles might provide the initial spark necessary for the birth of a universe.
So, Professor, does this mean we can say for sure that our universe was born from such a virtual particle or quantum foam? Or is it just a possibility?
It's a possibility rather than a certainty. Quantum mechanics shows that such a mechanism is theoretically possible, but that doesn't mean our universe definitely formed this way. We still don't have a quantum theory of gravity that operates at the Planck scale, so the true nature of quantum foam remains hypothetical. There are also criticisms. Some argue that virtual particles cannot form a permanent structure capable of creating an entire universe. Nevertheless, quantum fluctuations, especially those involving virtual particles, still present one of the most plausible scenarios for how our universe might have begun.
Professor, so far we've talked about how quantum fluctuations could lead to the birth of a universe. But what kind of scenario does this idea present for what came before the Big Bang?
Quantum fluctuations support the idea that there may have been an energy field existing prior to the Big Bang. In other words, the Big Bang might not have been an absolute beginning. Instead, there could have been a period dominated by vacuum energy before it. This idea is central to the vacuum genesis model, which suggests that our universe emerged from a fluctuation in the quantum vacuum. Stephen Hawking and James Hartle's no-boundary proposal also comes into play here. According to them, time and space may have had a different geometric structure before the Big Bang. Time didn't function in the classical sense. It behaved more like a dimension of space. This suggests that there was no before the universe because time itself began with the Big Bang. These scenarios assume that our universe was born from a quantum event. In this view, the Big Bang isn't so much a beginning as it is a transition point.
So, Professor, how widely accepted are these ideas in the scientific community? Is everyone in agreement on these scenarios?
No, not at all. In fact, most of these theories are still highly debated. Some scientists argue that quantum fluctuations aren't a powerful enough mechanism to create an entire universe. Critics of the vacuum genesis idea in particular point out that even a vacuum is already something, so it doesn't really explain creation from absolute nothingness. We're also at a point where quantum physics and general relativity haven't been fully unified. At the Planck scale, the laws of physics as we know them break down. So while these models are theoretically consistent, we don't yet have direct evidence to test them. This keeps the discussion in the realm of possibilities rather than scientific certainty.
Finally, Professor, do these theories give us a definitive answer about the origin of the universe, or is there still an unknown?
There's still a great unknown. Models based on quantum fluctuations and vacuum energy are among the strongest candidates for explaining how the universe might have emerged, but this doesn't mean we've solved the question of the universe's absolute beginning. There's still no answer to this. Where did the vacuum energy itself come from? This leads us back to one of humanity's most fundamental questions. What was there at the very beginning? Quantum physics gives us powerful clues, but to complete the story, we'll need more advanced theories like quantum gravity. Perhaps one day, we'll be able to solve this mystery too.
Professor, today we took a profound journey from the quantum vacuum to virtual particles, from quantum foam to what might have existed before the Big Bang. Learning that even what we thought of as nothingness is actually seething with energy was truly mind-blowing.
Yes, realizing that even what we call empty space is actually full changes our entire perspective on the origins of the universe. But let's not forget, this story doesn't end here.
Right. In the next episode, we'll explore another major theory about the beginning of the universe, the cyclic universe hypothesis. Could it be that our universe didn't have a true beginning, but is part of an eternal cycle? Did we emerge from the collapse of a previous universe?
In that episode, we'll dive into the idea of time's circular flow and the striking theories where universes give birth to one another.
So don't forget to subscribe and turn on notifications to catch the next part of this series, because this story is only just beginning.
You said you don't dance, but you move so. Your